Good afternoon. Welcome to Colloquium. Our speaker today is my colleague from the math department, Professor Healey. Team identifies as applied analyst. Is that right? Good characterization. Which in my eyes means an analyst who actually knows what each function space is actually good for, why it was invented, what is it useful for, what wouldn't be possible without it, and who grows the theory out of the problems for which he or she is trying to find the answer. I walked into his office 2 days ago asking to see his CV to do this introduction. He resisted for a while, but actually I got it. So I'm here to tell you that he started his path towards this day a long time ago. In particular, he got his double major in civil engineering and mathematics in the University of Missouri in 1976. You can see that he had divided loyalties between math and engineering at that time. He went on to get his master's degree in structural engineering and actually worked as a civil engineer for a while. Got his PhD in mechanics. Then from there on he was on straight and narrow. He did his PhD in mechanics in the University of Illinois in 1985. Did a math postdoc in Maryland with Stuart Dentman. And from there on he was fully in math with a briefest of detours for 20 years in theoretical and applied mechanics, which department he was a chair for 8 years here at Cornell. In these years, he was a very popular advisor. He had 4 chem graduate students and the number of the graduate students he supervised. His talk today here was also invited by the initiative of some of the chemisters who said that they wanted to hear him. I really enjoy working with graduate students who are supervised by him. I wrote a paper, co-authored a paper with one of them, and then finishing a paper with another. So really looking forward to the new graduate students he recruits so that I can write something with them as well. He earned a total of 4 teaching awards in all these years. And in 2009, when he won one of them, he was quoted in Cornell newspaper, giving a quote from one of his teaching evaluations, in fact. So one of the students wrote, "What I like about Healey is that he has opinions, some of which I do not necessarily agree with, and he is not afraid to express them." So here is Tim Healey and his opinions.
That's still my favorite. Thanks a lot for the kind intro, and that's my title, as you know. And here's a quick outline. I want to show you a little movie, and that'll, rather than trying to describe in words, give you immediately the idea of the problem I wanted to work on. I'll give you a little bit of history about this problem. It's a very popular problem. Lots of people have worked on it. I'll propose a new model. Talk about some computational results that I think demonstrate the goodness of our model. And then I'm not happy with that. I hope I have enough time to show you some existence theory. And there are some very cool, in my opinion, calculus of variations problems associated with that last one. And some of them I can answer, and quite a few of them I cannot. It's nice to have things to hope for. So let's see. Yeah, here's the movie. So this is a middle elastomer. Those are 2 straight edges being stretched out. And I guess the thing to notice from this little movie is that the wrinkles come and the wrinkles go as you stretch this thing out. And those are the fingers of András Sipos. He's my young colleague in Budapest. So he's the one that rigged this thing up so that he could, get it across to people. I wanted to show it again. Let's see. Anyway, you can imagine doing this with a piece of saran wrap yourself. You know
plastic is?
No, not exactly. It's some high-grade elastomer. I don't know, he spent a lot of money. He even gave me a little piece of it himself, but it's still in my drawer. Okay, a little history. The first guy, as far as I know, who noticed this phenomenon, this is sort of like anti-buckling, right? Buckling is when you press on something and it buckles out. This is being stretched out and it does something in the transverse direction. A guy by the name of Friedel, and there's a couple of more, in 2000, without much fanfare. But it got picked up by this group. This group also includes Mahadevan. I know some of you know Mahadevan. And they sold it big time. This was a big successful paper that appeared in Nature. And this impacted a lot of people. It got the interest of a lot of people, including me, you know, this Nature art. Just a couple of references for things that we've done on this problem. I put this slide up here to remind myself to tell you that if this sheet was on idealized curtain rods, when you pull this thing apart, it would just Poisson contract happily and there wouldn't be any wrinkles. So it's really important that this is totally clamped. You clamp on firmly and you pull it. It gives rise to an inhomogeneous, in-plane state that develops compression in the opposite direction, and that's what actually causes the wrinkling. Here's a little cartoon of the model. L is going to be my length, W is width, capital W. Sorry folks, that's for width. Little w, on the other hand, is going to be the out of plane displacement. And that's going to be the signature of wrinkling. W0, no wrinkling. W non-zero means wrinkling in this problem. This is a little two-dimensional sheet, so I'm modeling it that way. Omega is the region that it occupies before you do anything to it. Epsilon, that's a little epsilon there. I went ahead and blew it up so you could see it. It's epsilon times the length. So I'm imagining a very hard device. You totally clamp one side and you pull on the other, and you can tell the other end how far out you want it to go. It's an idealization. We call it a hard loading device. F is the name for...
Was that little letter in front of the L, capital L up there?
Yeah, that's the little epsilon. That's why I blew it up. It's little epsilon times L. It didn't come out so well. So that's why I went ahead. And this is going to be our macroscopic strain. You know, if you just treat the thing like it's a black box, that's our macroscopic strain. And F is the mapping that takes the planar domain and maps it into three-dimensional space. And I'll split it up into a couple of pieces. X is just the coordinate that it occupies here. U is going to be the in-plane displacement, and W is in E3 is pointing out of the board at you. Okay? And this is continuum mechanics notation, but this just means take the derivative. And if you take the derivative of the mapping, you get something that looks like this. This is the 2x2 identity. This is a 2x2, but this is a 3x2. That's the component that's representing coming out of the plane. But this includes the infinitesimal stretching and rotation that an element would have. So to get rid of that, you form something called the strain. And a green strain is defined this way. And what pops out when you do this, when you take this F transpose F, you get a 2x2. So this is a 2x2 strain matrix. We call it in continuum mechanics. And the Föppl approximation, which I'm going to get to right now, Föppl is part of the name Föppl von Kármán. And that's a very famous model that lots of people like. And Föppl gets his name on it because what he did was threw this nonlinear term out. He says that higher order term in the strain is not very important. And so let's just keep infinitesimal strain, as that's called, and retain this term. That's called the Föppl strain. And Linearized curvature, that's also in the Föppl von Kármán model. This is just quadratic approximation to the curvature. We would call it the curvature of the second fundamental form. And again, if you took the second derivative of f and write it out, you'll get a creature like this. If you let n be the unit normal on the deformed surface, then n dot del squared f really is, it has the components of the second fundamental form. And what you do in Föppl von Kármán is you approximate that by E3. So you're saying, like in this problem, little teeny tiny wrinkles. So there's not much of a change between the outward unit normal on the deformed surface and the undeformed. And that's how you end up with this as an approximation. And here's the Föppl von Kármán theory. Continuum mechanics people will recognize this. This looks just like the energy and linear elasticity. And the only reason it's not linear elasticity is because it has this Föppl strain tensor. So it does have one nonlinearity in it. That's that term right there. And a bending term, which also looks like linear elasticity. Of course, the weights are different out in front. And this is right out of Landau-Lifshitz. The total potential, then, you just integrate over the domain. This is the in-plane energy, and this is the bending energy. Of course, we have to impose our boundary conditions. The boundary conditions are one end is fixed, one end is pulled out kinematically. The top and the bottom is the laser not working very well.
I can see it. Okay.
But I really like this guy because it advances my slides. See if I can chew gum and rub my tummy at the same time. What's the circle and the line? It's too complicated for me.
You'll see when you press the button. It's broken. It's broken.
Thanks a lot. How many years were we colleagues? Just teasing.
But maybe you could point at symbols when you're interested, because I really can't see what you're pointing at most of the time.
Here, you just press harder. Press hard.
This one works.
Yeah, but it's hard to follow it.
Here, try this. Just press harder. I'll follow along. Top one. Top.
Top one?
There you go.
Okay. This is the in-plane part. This is the membranal part. This is the bending part. And listen, this is just some glorification. It's not that important, Steve. This is some glorification of 1/2 k delta squared. Everybody's had baby physics in this room, right? In high school. You know, the stored energy in a spring is 1/2 kx squared. This is a big generalization of that idea. This is called the Föppl von Kármán theory. The thing I want you to remember is that it has that approximate strain in it. We need to impose our boundary conditions. That just says what I was trying to say before. One end's clamped, one end you're telling the end what to do. The top and the bottom are free. Okay? So advance this way. This theory was cooked up by von Kármán. Your thing isn't working.
Press hard.
I'm doing it. This was cooked up by von Kármán. I read his memoirs. Fascinating. It's called The Wind and Beyond. Von Kármán was not a shy guy. He talks about when he cooked up this model, because in those days, I guess they had jet technology. This is like before the First World War. They had jet technology in Germany, and they handed it to the engineers and said, give us a plane with this thing. And the engineers at the time were civil engineers, and to civil engineers, we're both civil engineers here, there's no buckling. There's no buckling. I mean, in this building right here, if one of the columns had buckled out, we'd all run out shrieking, right? If we could run out. So von Kármán says the reason he cooked up this thing is because he wanted to demonstrate that buckling in an aircraft structure is fine, especially the panels. So you can make the thing extremely light, and buckling is okay, and he wanted to show that buckled panels are actually strong. So that's how he cooked this thing up. And look, in this wrinkling problem, the Föppl von Kármán model, I claim, almost always predicts wrinkling. What I mean by that is just about any aspect ratio, and it always gives a pitchfork when it does. And if you don't know what a pitchfork is, here it is. This is the famous Euler buckling pitchfork bifurcation diagram. I think we've seen the pitchfork a few times this year. I know my buddy Kielhofer was here. You certainly must have had a pitchfork, and I'll bet you could have had one.
Could have.
I'll bet you could have. And everybody's had Strogatz and Rand's classes, and you know what the pitchfork is. And what this represents is if you push on a rod, a column, if you push on it hard enough, it bows out. And it can bow out this way, and it can bow out that way, and that's what the two sides of this branch of solutions means. And in particular, when it bows out, it just keeps on bowing, and just keeps getting bigger and bigger and bigger the more you press on it. Lambda is like some measure of the amount of pressing. Okay, so listen. It's a really popular problem, and that Nature article got everybody off on the Föppl von Kármán model. It's a very influential paper, and they got it right out of Landau-Lifshitz. So if it's in Landau-Lifshitz, it has to be the thing to do, right? The problem is Landau-Lifshitz was written in the 50s, and it was translated into English in the 60s. And for aircraft panels, it's fine. You know, if I grabbed onto an aircraft panel, I can't stretch it very much. So small strain theory is just fine. So my first reaction with this was, we need to put finite strain and nonlinear elasticity into this membrane. So here's one thing you could do. You could use the exact strain without throwing that term out that Föppl takes, but still use the same model, the same energy. And then these things are really these two are more for the experts. You could treat it really like a good rubber model, and you get a neo-Hookean, or you could do even better. It's called Mooney-Rivlin. So these are more complicated, these ones. But actually, these were devised on biaxial tests on rubber. Did you know that?
No.
Yeah. Anyway, for bending, for this problem I'm talking about, the size of the wrinkle is usually the magnitude. It's the same as the thickness of the thing. So I'm not so worried about the bending. So this is a finite strain membrane, finite elastic membrane with small bending. One more thing. Just to show you quickly what the Euler-Lagrange equations turn out to look like. These are the equilibrium equations. So you take the first variation, you integrate by parts formally, you get a membrane balance law and you get a bending balance law. And it's very similar to the von Kármán equations, except this term would not be in the von Kármán equations. And that's really significant, but we don't have time to talk about that. The thing I want to bring your attention to is that the bending equation has h squared out in front of it, and h is the thickness. And these things are teeny tiny, and h squared is even teenier. So we're not going to be able to solve this problem in closed form, not even close. We're going to solve it numerically. And if you leave that little h squared in there in your finite element model, you are throwing out the baby with the bathwater. Because this is a beautiful elliptic operator. It will help do good numerics. And if you put, 1/10,000th out in front of it, you're kidding yourself. So that's not a good strategy. So instead, what we do is this simple little step. We divide this equation through by h squared and call this our new parameter. So instead of a teeny tiny constant out in front of the beautiful elliptic operator, we throw it all over on the right-hand side and make the right-hand side bigger and bigger and bigger. And that's how we tackle this problem. Okay, some computational details. We actually solved two different problems. Yes, sir?
Is there a physical interpretation of throwing the h on the other side?
No, it's just math.
Okay.
No, it's just math because
It's not like zooming in and looking at something more carefully?
I guess you could call it a rescaling thing. You could. It is some kind of rescaling. But we don't do it to the n-plane equation. We just do it to the bending equation.
But you just multiply an equation by a constant. You haven't done anything. Why does it do anything? Unless there's some other equations.
Great elliptic operator, right-hand side. Get the right-hand side bigger and bigger and bigger, as opposed to a singularly perturbed numerical problem.
Just how you orient the numerical problem.
Yeah.
It's not the size of the term. It's that you do this.
And I'll show you the diagrams. I mean, in some sense, we got lucky because I can't do any a priori estimates on this thing. I don't know how to do it. Anyway, bear with me. So we solved actually two problems. We said to ourselves, like any good finite element person would do, this problem has lots of symmetry. It has two reflection planes of symmetry. You can see by the experimental results the wrinkles behave that way. So you assume reflection symmetry here, and you assume reflection symmetry there, and you solve the problem on the quarter domain. On the other hand, you could have taken this thing and flipped it over. So it always has reflection symmetry this way, but it also has a flip symmetry like this. And if you do that, you get what's called anti-symmetry over here. Whatever's happening here, you flip it over to get that one, and then you reflect it over. So we solve two separate problems. We use finite elements. Anyway, the important thing here is symmetric and anti-symmetric. And here's my numerical continuation scheme. I actually have three parameters that I'm going to use, but I'm only showing two of them. Yes, Steve?
So in that previous slide where you talk about the symmetry, are you saying you're going to assume solutions in the class that respects these symmetries?
Yeah.
So you're not gonna-
And you'll do that by just making a finite element model of the quarter of the system.
Yeah.
And you arrange things so that the boundary conditions preserve reflection symmetry. And same here. But then over here you arrange different boundary conditions that preserve the, and if you would look down the eye of this axis, one of them is reflection symmetric and the other one is flip symmetric. Mm-hmm. So we go off and solve those two separate problems.
And you're interested in those symmetric solutions because in the experiment that's what you see?
That's a very good question, and we'll come to that point. Because there's a real surprise sitting here that I don't completely understand either, but I'll get to that. Anyway, here's just kind of a grand plan of how we tackle this problem, and there's one more parameter too. There's the aspect ratio. So there's actually three key parameters. There's the macroscopic strain. That's a measure of how much you pull this thing out. There's my new parameter, which is 1 on h squared, and then there's the aspect ratio. And the way we got started, you pick a relatively large thickness so that there's no wrinkling, and you impose a modest strain on it. This gives a planar solution. So that's sort of coming out here onto this one. And then you fix that, and now you start increasing this. And this is kind of where we got lucky. All the branches do go this way. So you really do get out there. When this thing's getting large, h is getting incredibly small. And look, here's what happened. So this is actually the very first model that I showed you, the model with just putting in the correct strain measure with linear elasticity. So it looks just like Föppl von Kármán, except it has an exact strain measure in it. And the red and the blue are the solutions to the symmetric and the anti-symmetric problem. And this is, maximum W versus my 1 on h squared parameter. So this is the continuation, this is this continuation going on. And they're sitting right on top of one another. And actually, the very first student that I had that worked on this was poor Rondin Cheng. Some of you may remember Rondin, really sweet kid. And he came to me and showed me some of this stuff, and I said, that's wrong. He said, why? I said, that's wrong. There's not enough symmetry in this problem. This is a simple symmetry group. It has the reflections of the rectangle and has the rotations, and that's it. And all the irreducible representations are one-dimensional, and there's no reason for a degeneracy like this in this problem. You must have somehow made a mistake. And he hung his head down and walked off, and I don't know, doubled the mesh size. And then he came back, a week later, and they were even closer together than they were before. And here's what happens. So these are like the first 4 bifurcating branches, and red and blue really do live on top of each other. I think this particular rendering, we don't really have the fine mesh that we finally ended up with. So the first branch, what do I mean by that? This is the first branch. It's the first one that occurs. It's stable. It's the stable one. Because, by the way, all I'm interested in are solutions that at least give local minima to the energy. Those are the ones that you're going to see. The rest of them you will not see. They might lead to interesting dynamics, but you're not going to see them.
This is the picture before is the pitchfork, is that right?
Yes. Yeah, there's two sides to this, but on top of that, there's the solution to the symmetric problem and the solution to the anti-symmetric problem.
So down the middle is the
I mean, there's not enough dimensions to show it as a pitchfork, but yes, it is. The first branch is stable. Was someone about to ask something?
Yeah, I was going to just get back to that again, because this is a projection.
Yeah.
And so,
Yeah.
just tell me again, what's sticking in the same direction if you remove projection?
Well, I mean, all I'm doing is plotting maximum W. There's a solution to the system here, and there's two sides to it. If there's an anti-symmetric one on one side of the bifurcation, it looks like this, and on the other side, it looks like that. And those are the two sides of the pitchfork. But the pitchfork is getting projected in this picture.
But you have 2 pitchforks, because you've got a dot.
Yeah, and that's
And they're lying exactly on the top of each other.
Right, and those are
And the dots you're going to tell us about.
The two solutions are not the projections of the two sides of the pitchfork. One of them came from symmetric boundary conditions, and one of them came from anti-symmetric boundary conditions. So one has reflection symmetry, and one has flip symmetry, and they're totally living on top of each other in this problem. And then
Dots come later. Can you tell us about those?
what dots?
Is there a dot? There's a circle and a dot? It's like a
One of
dot.
them's anti-symmetric, and one of them's symmetric. One of them's the
Some
symmetric.
special symbols, like go to
Symbols.
9.
Where?
Go to 9 and go straight up.
Oh, yeah. Those are some ones where we're going to come off of, but I haven't gotten there yet.
Okay.
Yeah.
And then there's some stuff about 1. If you go right up to 1, it looks like a circle.
This is just the data that we use to actually make these computations. So it's like 10% strain, Poisson's ratio is 0.45, and beta is S some
Next to
aspect.
.008, you think?
Here.
There.
Yeah, those are just a couple of solutions that we'll pinpoint later.
Is there some sort of symmetry that maps symmetric boundary conditions to anti-symmetric?
Say that again?
Is there some sort of symmetry of the equations that map symmetric boundary conditions to anti-symmetry?
Yeah, sure. This problem has the complete symmetry of the rectangle, the geometric symmetry of the rectangle. So it has the reflection symmetries and it has the flip symmetries. I don't know, that group certainly has a name, DN2, or I don't know. There's some name for it.
What I think he was asking is there some way of thinking about it that the two solutions are the same?
Which ones?
The antisymmetric and
No.
symmetric.
No. That's my point. No. It's a simple little group that has one-dimensional irreducible representations. So no, you would not expect this. I mean, take a simple problem on the interval, a simple little ODE that has both reflection symmetry and flip symmetry and anti-symmetry. We call it that in civil engineering. No, you wouldn't expect those to have the same. You wouldn't expect those to have the same solutions in general. No. Anyway, first branch is stable. Okay, but it's orbitally stable. What does that mean? Every reflection symmetric solution has a zero eigenvalue with an anti-symmetric eigenvector and vice versa. So these are two solutions living on top of each other, and they're orbitally stable in the sense that they do have a zero eigenvalue associated with the direction of the other solution. Like a problem that has rotational symmetry. This doesn't have rotational symmetry. Anyway, it's a mystery for now. And it's not really my point, but we've spent some time on it, it's fine. So look, here's what we did. We said, well, let's watch those two zero eigenvalues as we travel along these two branches. Each one of them has a zero eigenvalue, and let's watch them as we move along. So that's what we're doing in this diagram. It's all projected down on a line now, but we're just watching what happens to the zero eigenvalue. And, you know, for a crude mesh, they start to pull apart from one another. But the more and more refined you make the mesh, the longer and longer those two zero eigenvalues stay together. So Ron Bin was right. Ron Bin, the more he refined, the more and more these things fell on top of each other. No symmetry explanation. What's going on? The best I can do for the experts is tell them I have a hand-waving answer for that. It's asymptotics of a beam on an elastic foundation. This is actually in Mahadevan's paper too, the beam on the elastic foundation analogy. And what happens is, as the thickness goes to zero, for all practical purposes, the width of the thing is going out to infinity. And you end up with a beam on the elastic foundation of infinite length, and a beam on an elastic foundation of infinite length. The symmetric and the anti-symmetric solutions give the same.
There's sines and cosines.
Yeah, they are. And every phase angle in between them, because it's an autonomous system on the real line. So it's some kind of weird asymptotic symmetry. Anyway, that's still not my point. I could give a whole talk on that stuff, but that's not my point. Listen, so here's the finite elasticity models. And here's the solutions that we found. I picked some data very similar to what's in the Mahadevan model to get started. Blue is the new model, the first one that I showed you, and purple is going to be what Föppl von Kármán says. And here's what we get. So remember, this one is Föppl von Kármán. This one is ours. So now,
I'm sorry, did you do that with your finger? I couldn't see what you pointed at.
Let me go
Top,
back.
did you say top and bottom or something?
Wait a split second. So you were asking me what these guys were. So see, we come along the first branch, and we pick some solutions that we like. What does it mean that we like them? Like this one right here.
Can't see.
Not pointing at anything that we can see. Just point with your finger.
The light's not on.
I'll do it. I'll just stand here. You tell me what to point at.
Sit down.
Well, you're not. I can't see. I'm not getting to talk.
Actually, you haven't hardly missed anything yet. You haven't gotten anything.
It's a psychological problem, Tim. You're staring at the thing, so you see the red
You
dot.
know where you're pointing.
We know, but we can't see it.
These dots. Somebody asked about these dots before. These dots represent very fine thicknesses. This one's fine, this one's finer still, this one is unbelievably fine, okay? They're stable solutions. So we picked these three. Now you freeze the thickness that you're happy with, and then, let's see, yeah, then you do this. Now you got the thickness you like. Now you turn on epsilon, and you find your solutions in a very efficient way. So when we did that, this is what we get. So this is now epsilon on this axis. This is the amount that you're pulling this guy by. Here's what Föppl von Kármán says. Föppl von Kármán says, okay, for a little teeny tiny bit here, you pull on it and nothing happens. Wrinkles emerge, and then the wrinkles continue to grow, just like Euler buckling. This is not what we found. You pull on it, the wrinkles develop, you continue to pull on it, they max out at a very small value, and then they eventually go away.
And your movie was dead clear on that.
Just like the movie.
Yeah.
These are just pictures of what it looks like along the horn here. So here's the first one right here. This is what it looks like. Here's the next one. Here's what it looks like. This is what it looks like. The thing to notice about these is that the nodal pattern stays put. I don't have a proof of why that's true, but as you move along, the number of wrinkles stays put. And I have several pals who've done experiments on this, and they tell me that's what they really like about this result, because that's precisely what they see.
But you could change it.
Change what?
I mean, you don't think you could start with a different perturbation and get a different solution?
No.
So you think that's a unique solution?
It's not unique, but it's stable.
So you could put a different perturbation.
So there are people who have done dynamical models of this, and get the same thing. So they sort of use like gradient descent dynamical models. I don't have a proof, but
Is there an asymptotic expression for the transverse profile of the amplitude of the wrinkles?
I mean, these are purely numerical, and there's no hope in this problem of doing anything in closed form, but they sure look like exponential envelopes with sines and cosines inside them, don't they?
Yeah, or a Koch profile.
Okay, so that gives you a flavor for how we're capturing the right behavior, okay? But it's even better. It gets even better. So now what we said is, let's do continuation in aspect ratio. I don't know, Amy, this thing is moody as hell. Oh, it fades out. I see. I hold it and then it goes away.
Works for me.
You talk faster than I do. Anyway, we're going to use this as a continuation parameter. So here's what happens. So, I don't know, beta is our continuation parameter. So by the way, we don't go back to square one and make it a different rectangle and do the whole bloody thing. Once we have a solution, we can perturb off and move in the aspect ratio direction with our solutions. So look, here's, Steve, can you see that red dot?
Yes.
Okay, so here's what we get when it's 20 by 13.3 instead of 20 by 10 like before. And we get nothing. We get no wrinkling. But von Kármán says, oh yes you do, and it continues to grow as you pull on it. Okay, and then move it over a little bit to 12.5. Something pops up that looks a lot like what we had before. There's the precise one that I showed you before. And then as you make it more and more rectangular, it goes away again. But von Kármán is always sitting there with his. So it's not only that the von Kármán thing gives a bogus prediction, it also tells you that you almost always get wrinkling when you don't.
But if you have a very long one, the von Kármán solution is presumably just wrinkles at the end and not wrinkles in the middle, isn't that correct?
No. The von Kármán solution is pretty much linear elasticity with a little tiny perturbation on the top of it.
And but you said it's the boundaries
that cause the buckling.
Yeah.
If you have a very long thing, the middle of it doesn't see the boundaries.
That's right.
And so there should not be wrinkles in the middle anymore.
Yeah, it's like you're getting the Poisson effect but you need finite elasticity to
So
see
we're saying
that.
the von Kármán solution,
Well, the von Kármán solution gives the same phenomenon. It gives the wrinkles.
only at the end though,
How do you know that?
because you told me at the beginning, you said that if you don't see the boundaries, you don't have the wrinkling. If you have a very long thing, the middle of it, the boundaries are gone. And so there shouldn't be wrinkles in the middle if you have a long thing.
There isn't.
Right, so that it
But my point is you need finite elasticity to do that.
well, what is, but you said the von Kármán solution says that there are wrinkles in the middle even when it's long?
Yeah.
So St. Venant's principle is violated by the von Kármán's, by their theory?
I don't know anything about St. Venant's solution for the von Kármán.
No, it's not the solution, the principle, that the ends disappear.
So like if you take like a chunk of metal and you put a concentrated force, and when you go away from where the force is applied, it's, you know,
This isn't linear elasticity.
And so can you just, you've told us a few times, but please remind us, the basic mistake that's being made in von Kármán theory is the neglect of bending stiffness? Is that the problem?
No.
What's the real problem?
They're not accounting for the stretching correctly with finite elasticity. So it's almost like linear elasticity with bending. That's the von Kármán equation. And it is nonlinear. It has a nonlinearity in it. But it's the coupling between the membrane and the outer plane that gives the nonlinearity.
That's in their model?
Uh-huh.
Yes.
And so what we have is finite exact elasticity for the in-plane part. And when you do that, you get the thing coming and going the way you're supposed to. And you can make a movie out of it. Oops.
So you're saying you kept the membrane nonlinearity that they got rid of? Is that right?
They didn't get rid of the nonlinearity completely.
They had two nonlinear centers, but they killed one.
Right.
But you kept both.
They're not using finite elasticity for the membrane part.
Right.
That's my point.
Right.
And you need finite elasticity to get this phenomenon. And by the way, this has a name too in bifurcation theory. It's called the isola center bifurcation.
Sure.
And there's an extra parameter floating around in it, but this is its normal form. There's always the trivial solution, and then there could be non-trivial solutions, but it's sort of like a circle. And then as you change this value, it goes down to a dot, and then it goes away. And that's exactly what we see on both ends. If it gets too squat, there's no wrinkling. If it gets too rectangular, there's no wrinkling. So this is like one end of the isola. Oops. There's the middle of the isola, and there's the other end of it going away. Okay. So listen, we were also able to take all of our models, all three of them that I showed you before. Two of them are really sophisticated elasticity models. One of them is just throwing the other nonlinear term back in. And then blue here, unfortunately, we've changed colors, is the von Kármán. So this is a stability boundary. Here is the aspect ratio, and here is the stretch, the macroscopic strain. And what these are telling you is that on one side of the curve, you're unwrinkled, and on the other side of the curve, you are wrinkled. You're stably wrinkled, like what we've been talking about. And here's von Kármán. So this is aspect ratio right here. Sorry. Put the handy slide if I can. Wow. Guess not. This is aspect ratio. So what I was doing before was making slices through here and showing you what the solutions look like as you go through aspect ratio land. And the finite elasticity models are all closed curves. So if you slice through here, you'll get one of those diagrams that I was seeing before. Whereas if you slice through up here, you'll get the von Kármán diagram. And there's von Kármán way up there at these aspect ratios, and down here giving bifurcations as well. And here's just two different thicknesses showing the same thing. And these are just showing you what those slices look like. So here's the beta equals 1.4 in one of them. von Kármán is the only one who's alive. Then you change it to beta equals 2, and they all come alive. Oops. Beta equals 2.75. Only my modified one is active. And then finally, if you get big enough, again, the only one that's active is von Kármán, incorrectly active. So listen, these two right here that almost live on top of one another, those are the really good elasticity models that come from true experiments on elastomers. So I really trust these diagrams. The red one was the first one we tried, and those were all the solutions I was showing you. They capture the right qualitative behavior, and it was enough to get people's attention. But actually, you can see they're not so accurate. And by the way, it's well known that when you put in finite strains with linear elastic constants, we usually call that like a Saint Venant Kirchhoff material, and it's a well-known piece of junk. We got away with it semi because it's way out there on the tensile. It's on the tensile end, but it's a well-known piece of garbage in general.
So how much of the difference is the constitutive law and how much the finite straining boundary?
Well, all of the closed curves are the finite strain models. So they're doing the right thing. If you slice through it at a given aspect ratio, it'll give you that diagram like I showed before. And if you get too small or too big in your aspect ratio, you won't see it. So the red one was the solutions I was showing you before, and they qualitatively do the right thing, but I don't have the confidence in them that I do with these two. These are
But the green ones are more fancy constitutive law?
Yes, those are the neo-Hookean and again, those things were actually constructed from biaxial rubber tests.
And in kappa, if we reduce kappa sufficiently far, these just keep going down. How do those pictures deform? Do you deform kappa?
But that's just a finer and finer and finer thickness.
So it suggests.
Not you mean when you let kappa getting bigger and bigger.
Oh, either way.
Yeah. Well, I mean, they'll eventually you won't have anything thick enough to wrinkle if kappa gets small enough as h getting big.
But look, from those that there was some influence of kappa on the size.
Well,
of the
there
isomers.
is because that's the thickness. Yeah. So the number of
uninteresting.
the number of wrinkles will change and blah blah blah. Yeah, but the phenomenon will not. That's right. I can't prove it. This is purely computational. And these are just some solutions with the more sophisticated models, but you still see the same
They're all
phenomenon.
anti-symmetric, right?
There's one of those. Yeah, these are asymmetric. These are the flip symmetric. The whole symmetry asymmetric story is really interesting, but that's not what I want to do now. Here's a few people who have done some things on this problem with more sophisticated models. Nayar et al. Actually did things before us. And they used abacus, they used a neo-Hookean model, and they used a large bending. So it's model-wise, it's on par with some of the stuff we're doing. But this is a canned program. They had to put in imperfections and do fishing, so approximately they found the same thing we did. But they just fixed the aspect ratio and they get this kind of trend. They didn't investigate aspect ratios or anything like that. And then these are the guys who did the dynamical simulations that I was talking about. Shibosh, that's the guy whose fingers you were looking at the very beginning. He has done experiments himself before the good material that he was showing you before. And he got some really cool results with some elastomers that have something called the Mullins effect. That's kind of a permanent strain effect. So you stretch it and it doesn't go all the way back. And he has some really cool results, like you pull on it and it doesn't wrinkle. But then when you release it, it does wrinkle. So we're not done. There's more to do on this problem. Okay. Oh, there was a slide. just advertising the fact that the isola-centered bifurcation is really ubiquitous. And this really is a change of phase problem. The two, it's almost like sawtooth, little rounded at the sides, the wrinkled patterns. These are acting like the two different phases in this problem. And it happens all over the place. It happens in Cahn-Hilliard models, two-phase shaped memory alloys, lipid bilayer membranes, et cetera, wherever you have a setup that's a lot like ours, where you have a convex term in the higher gradient and a non-convex lower order term. Anyway, I just mentioned that in passing. I've got 10 minutes left to talk about some existence questions, so I totally want to switch gears. Why rigorous existence? I love this quote. It's from Courant in his book Dirichlet's Principle. And the essence of it is empirical evidence doesn't mean existence. And the only true test of a theory is actually to prove an existence result. I agree with that philosophy. So I have a new model. I have a finite membrane elasticity model with small bending. How do I know that I'm not just doing a numerical poof here? So what about a rigorous bifurcation analysis? Couple of difficulties. First is that there's no homogeneous solution to perturb off of. That's what you do in a bifurcation analysis. You got the luxury of some family of easy solutions that you can write down, and you want to know, are there any solutions that bifurcate off of that? Our primary solution is planar, but it's not homogeneous. It's a nonlinear finite elasticity problem with imposed boundary conditions on two sides and free on the other. Forget it. Also, there's a real mathematical reason why you cannot do any rigorous bifurcation analysis. That's because in this problem there are true corners. What I mean by a true corner is that you can't extend by symmetry and use Fourier methods or something. This corner up here is totally clamped on one side and totally free on the other. There's definitely a singularity out at the corner. And for you that know, you analysts in the room, that means you really do need to work for your in-plane displacements in a space like W1P. And I don't know if you've ever been down this road before, but I know there's one person in the room who has. Differentiability and continuity and things like that, when you're in a nasty space like this, is anybody's guess. So there's really no way, as far as I can tell, to do a rigorous bifurcation analysis in this problem. So, what else do we do in this business? We try rigorous energy minimization. So, I'm going to generalize a little bit, but it's based on all the behavior that we saw in the earlier models where we were doing numerics. So K is my approximate curvature. K is my approximate curvature, just like I was doing in the von Kármán stuff. C is just what it was before. It's a 2x2 strain tensor, and its determinant speaks for itself, and the square root of the determinant is actually the area ratio. And if you go back and look, you'll see that powers of 1 over the determinant were appearing in my energy back when I gave you my models 1, 2, and 3. I don't want to back up. I'm running out of time, and I want to get to the punchline. So this is not some gratuitous thing. This rears its head always in finite elasticity. This thing, it's the area ratio. And in particular, you don't want the area ratio going to 0 and becoming negative. You're not doing realistic physics anymore if you do that. So what are my assumptions that are kind of gleaned from what I was doing before? I would like this function, let's have it be non-negative. All this says is that everybody's relaxed in the flat state. This second term right here. I want it to be convex in this curvature measure. That's how the von Kármán model was. And I'm going to say that if I take this pair, you know, B is a placemaker for, a placeholder for the determinant. If you take this pair into this function, so just think of this function as a function of those two variables, I'm going to assume that it's convex. That's actually called polyconvex. It's a common thing that we use in elasticity. And there's a remark at the bottom. This is actually much weaker than convexity. And in fact, you cannot have convexity. You'll get all kinds of crazy things if you were to insist on something like this. So you get away with this in vector-valued problems. And this is a glorious vector-valued problem, this one. So I'll assume that. That's called polyconvex. And by the way, my models 2 and 3 that I showed you earlier satisfy this condition. And then I'll also need a growth condition, because I'm going to try to argue like the Weierstrass function takes on its minimum on a compact set. I'm going to try to argue that way. So I have to have some kind of growth conditions like this. And again, my models 2 and 3 satisfy those. And then lastly, I'll demand that my energy blow up to infinity as the area ratio goes to 0. That's to prevent this thing from collapse, the area, little local area to collapse on itself and worse, pop out on the other side. Infinite energy density for the area going to 0. So the problem then is to minimize this energy over some admissible set. W, remember, is the out-of-plane displacement. It has a generalized second derivative. U is the in-plane. It has a first generalized derivative. And I have to keep track of what the determinant is doing too. This is my admissible set. And I'll have my mixed boundary conditions like what I had before. And I also want the area ratio to be positive in this admissible set. And 3, that was my growth condition. That's enough to show that the energy blows up to infinity as the norm of my test function goes off to infinity. So my V has to go like this as you get out bigger and bigger. And that says that any minimizing sequence is bounded. This is a reflexive Banach space, this triple of these guys. And so I know I have a weakly convergent subsequence. And then the convexity assumptions actually tell me that this functional is weakly lower semi-continuous. That's a mouthful, but continuous is too much. And roughly speaking, this is a cartoon. Lower semi-continuous means that the closed dot is always down here and the open dot is upstairs. Of course, you can't see it that way. F is sitting in a function space. It's a cartoon. And that gives me a theorem. It says that V actually does attain its minimum at somebody inside my admissible set. I can prove that. And here's a question. As I said, there's a bunch of them that I can't answer. One of them is, once you get that energy minimizer, is it a weak solution for the Euler-Lagrange equation? It means, can you take a rigorous first variation? I don't know. And I'll tell you this, if you think it's easy. If K is identically equal to 0, this is a hard, open problem of nonlinear elasticity. If you could answer that question with K identically equal to 0, you won't get one of the Clay Institute prizes, but I guarantee you'll have offers from 9 or 10 of the best places on earth asking you to please come and work at their university. Is it the same here with K not equal to 0? I do not know. I think there's a chance. With K not equal to 0, I think there's a little bit more room than there is when you're totally constrained in the plane, but I don't know the answer to this question. And then here's another one that's pertinent. Suppose you weren't just interested in wrinkling. Suppose you were interested in a big floppy thing with a little bit of bending stiffness, and you impose something on it, and you want to be able to get the existence of exotic shapes of this thing. So now you can't get away with using the approximate curvature tensor, or the second fundamental form. You need the real McCoy, and this is what it looks like. And so the question is, does F attain its minimum in some admissible set like A before, where now K is living inside an LP space with P bigger than 2? And I don't know the answer to this question either, but there is a paper by Langer in 1985 that's kind of along these lines. He can do it, and the answer is yes, but he does it for fixed global area and no membrane elasticity. It's a differential geometry paper, and in fact, if you look at it from a physical point of view, he has fluidity. So he takes a minimizing sequence and he's free to mix it up because it's a fluid to actually show that the thing attains its minimum. This is a piece of rubber, man. There's no mixing. And just to give you a clue about that problem before I stop, this is just a remark. If you use the full second gradient in lieu of k in my question before, this is called second gradient elasticity now, then attainment of v for f in a space like this with p bigger than or equal to 3, it's a textbook problem. You can study up in Evan's book for a couple of days and figure out how to make something like this work. And moreover, if the stored energy grows fast enough, as beta goes to 0, beta was the determinant going to 0, we actually obtain weak solutions to the Euler-Lagrange equations. By the way, this is not a textbook question, but I know how to do that. So why am I telling you this? Because I'm trying to give you a clue as to why this problem is so hard. You're only dealing with a piece of the second gradient here. The rest of the second gradient is free to do what it wants when you have a minimizing sequence. So that's the source of the difficulty. Whereas over here, you got the whole enchilada. It's not a problem. It's just a standard problem in W2P. Again, back over. Oh, I gave away my punchline. Over here, you're just taking a piece of it. Hey, listen, thanks. And thank you, U.S. taxpayers. Thank you for your attention. That's the end of the talk. My mommy always asks me, my mommy's still kicking. In fact, I just went and celebrated her 85th birthday with her last weekend, but she always says, so where is Cornell sending you now? I say, Mom, Cornell is not sending me anywhere. I said, no, and they never have. You do. Thank you very much. Thank you, taxpayers. What are you talking about? What are you talking about?
What if you started with a square instead of a rectangle? Then you would expect to see these bifurcations be on the same, wouldn't you?
No. If you start with a rectangle, you don't get wrinkling.
Square.
I mean, if you start with a square, you don't get wrinkling. There's some kind of asymptotic limit to the whole thing. I mean, at least that's what the numerics suggests. I mean, that's the problem with numerics. You can't prove anything. You see trends, and but it seems like the answer is no.
And how do they scale when you increase the size of the rectangle in both dimensions of the same by proportional factors?
I don't understand the question.
The wrinkling occurs in a compact region in the middle of the
Apparently.
fixed size independent of the dimensions of the membrane.
No, that's not true.
So how do the dimensions change of the area that wrinkles as you?
I have no idea.
Maybe a related question.
Yeah.
You said you take a long, narrow one, and in your theory, you pull on it and it doesn't wrinkle, and in the von Kármán theory, it does wrinkle.
Right.
I think that if you look at the von Kármán theory, you'll see it wrinkles at the ends and not in the middle, but you're not sure.
Yeah, I'm not sure.
But isn't it true that the von Kármán theory should be a good approximation of your theory for small strain?
Yeah.
So shouldn't your theory, if the von Kármán one wrinkles when it's long and narrow, shouldn't yours wrinkle for a small strain when it's long and narrow?
It does.
At least that it doesn't wrinkle.
Just on one side. Oh, I see what you're saying. Yeah, in that case. Yeah.
If you have a long narrow one, you get no wrinkles.
No,
ever.
only when they overlap. Only when my regions overlap do they live on top of one another over on this side. His is going like this, and mine is.
You said yours disappears when the aspect ratio.
It does.
So the aspect ratio is long.
Right.
You pull it a little bit.
Right.
Von Kármán's theory says it will wrinkle.
Yep.
Yours says it won't.
Eventually. it moves way out, because I don't know if you remember that curve.
Okay, so it's no longer small, we're out of the regime of its validity.
Oh, what am I doing? I'm going in the wrong direction.
What were those for?
Exactly.
I can show it to you.
Like
Oh, there it is. Yeah, so this is really,
So as you wouldn't expect the von Kármán theory to be good over there.
yeah, so these guys, the pitchforks are showing up out in infinity or something, and at least that's what
And
they're
a small strain, the theories do all line up
Right,
and agree.
yeah.
Did you keep the E3 assumption in your theory? I can't remember.
What's the E3?
So using the surface normal, you said the assumption was that the E3 vector was
That's always the same in all of the models.
in yours too.
Yes.
But in the question you posed, second to last slide, you said you proposed updating that.
Yeah, suppose you wanted to,
No, I understand.
suppose you weren't, that's because I like this model for wrinkling.
Right.
But suppose you wanted to have a theory for a completely flexible,
Right.
small bending stiffness creature.
But the reason I'm asking this question is wrinkles in the video at the beginning look big.
They're not. They're not. It's an incredibly small scale.
Really?
Yeah, it's just blown up so that you can see it with the eyes. The magnitude is the same order as the thickness of
Okay.
the wrinkles. They're like twice or
Okay.
2.5. No, they're little teeny tiny.
The video
No,
looked
the
big. Yeah.
curvature is incredibly small.
Okay.
Yeah, so no. Yeah. Yes.
Has any been numerical approach with the full bending?
Not that I know of. I mean, there's all kinds of shell models out there, but I guess even in principle in Abacus, there are finite strain, large bending models that you could take that element out of the library and not even write down a single equation and just put them together and press the button and get solutions for them. That's kind of how Abacus works. It's kind of how they all work. You just go to the element library. And even Abacus, you don't even need to go to the element library. You can write your own subroutine and plug it in to the big. So in principle, it's out there, but I don't know if anyone has done it. Yes, sir.
Isn't von Kármán in some sense the grandfather of the Center of Applied Mathematics? We still have a Bill Sears Club. We had for a while a Bill Sears Club.
We do have
We still do?
Yeah, we still do.
And wasn't Bill Sears a student of
Was
von
he von Kármán? Probably.
Yeah,
That's right.
So anyway, I wanted to mention, I heard von Kármán so much, I wondered.
Yeah.
a little history.
Yeah, and his memoir is just a fabulous read. It really is. It's a real gem.
What's it, Through the Wind and Beyond?
The wind and beyond, the hot wind and beyond. He's not a shy guy. You know, and the punchline to that story was that his analysis of the plate buckling, and he shows that plate buckling is good. That led to the proper design of planes, but it came after the First World War, and then everybody jumped on that bandwagon and made very flexible, strong. I mean, I think if you use your imagination in a windy day or a stormy day, I think you can see the little ripples kind of coming and going on the top of the wing as it does this. Yeah. I mean, planes are really flexible. But imagine if the Germans had the jet plane technology in the First World War. What's that?
Or earlier.
Yeah. Okay, great.